Can an artificial intelligence system be accurate and still be unfair? This video explains how algorithmic fairness measures help you detect bias, compare fairness with accuracy, and apply practical interventions. It also follows real examples, tools, and lessons from finance, healthcare, hiring, and law enforcement. Fairness metrics evaluate algorithmic fairness uses metrics and techniques to evaluate and address bias in machine learning models. Its aim is equitable treatment across demographic groups. The idea also connects artificial intelligence systems to ethical and societal norms. So, fairness is not only technical but also social. 0405. Fairness measures are used to assess bias in model outcomes. The material names, statistical parity, equal opportunity, calibration, demographic parity, disparate impact ratio, statistical parity difference, and equal opportunity difference. These metrics let you compare how a system performs across different demographic groups. Individual fairness says similar individuals should receive similar outcomes. In a hiring algorithm, two candidates with similar qualifications should have the same likelihood of being selected. The challenge is that defining similarity can be subjective and depends on the context of the decision. Group fairness looks at outcomes across predefined groups. A common example is keeping loan approval rates similar for different racial or gender groups. This approach can still miss disparities inside subgroups, which the material describes as fairness gerrymandering. Causal fairness focuses on whether sensitive attributes influence outcomes through unfair causal pathways. One example is loan approval, where gender might indirectly affect decisions through income. This approach can be powerful, but it needs detailed knowledge of causal structures, and that is not always available. 0405. Pre-processing methods address bias before model training begins. Techniques include data rebalancing and removing sensitive attributes or their proxies. An example is reweighting underrepresented groups in a hiring dataset so the training data reflects more balanced representation. In-processing methods build fairness into the training stage itself. The source lists fairness constraints, regularization terms that penalize unfair outcomes, and adversarial learning to remove bias from sensitive attributes. One example is training a classifier to reduce accuracy differences between demographic groups. Post-processing methods change predictions after a model has already been trained. They can calibrate decision thresholds for different groups or rescale probabilities to support equitable outcomes. A loan approval model, for example, can adjust thresholds to equalize acceptance rates across genders. Fairness and accuracy often pull in different directions. Improving fairness can reduce model accuracy because fairness constraints may override purely performance-driven optimization. The material frames this as a balance shaped by societal values, application context, and the priorities of those affected by the system. Constraints shape results. Social values guide choices. A hiring algorithm trained on historical data may maximize accuracy and still favor male candidates because past hiring was biased. In lending, an accuracy-driven system can reject more minority applicants, while a fairness-driven system may slightly increase default rates but improve trust and regulatory compliance. The process starts with data analysis, where you examine imbalances and use visualizations to detect disparities. Next comes metric calculation across demographic groups. Then you apply bias mitigation through pre-processing, in-processing, or post-processing, and finally recalculate fairness metrics and track progress with dashboards. Several tools are highlighted for fairness work. AI, Fairness 360 detects and mitigates bias with pre-processing, in-processing, and post-processing methods. FairLearn supports fairness assessment, mitigation algorithms, and dashboards, while What If Tool, Themis ML, and Scikit Fairness add visualization, bias reduction, and comparison support. After reweighting the dataset, the ratio rose to 0.8. One example uses loan applications with income, credit score, and demographic information. Minority applicants were underrepresented, and the disparate impact ratio came from an approval rate of 0.6 for minorities compared with 0.85 for non-minorities. The source describes using FairLearn and AIF 360 with a practical workflow. You load a dataset, pre-process it, train a baseline model such as logistic regression, calculate fairness metrics, apply fairness-enhancing techniques, and then re-evaluate the model after intervention. Effectiveness is measured by comparing fairness metrics before and after changes. In one example, the baseline model had a male approval rate of 70% and a female approval rate of 50%, with statistical parity difference at 0.2. After intervention, rates moved to 65% and 62%, and the difference dropped to 0.03, 0.4, 0.5. Fairer healthcare with targeted debiasing. Two healthcare examples show how interventions are applied. For patient readmission prediction, minority groups had higher false negative rates, and FairLearn reweighting reduced those disparities. In disease diagnosis, women experienced higher false positives, and adversarial debiasing in AIF 360 improved fairness while keeping similar diagnostic accuracy. In finance, loan approval systems discriminated against minority applicants because training data was biased. Reweighting with AIF 360 reduced disparities, but default rates rose slightly. In healthcare, in-processing adjustments with FairLearn improved diagnostic rates for underrepresented groups, with a minor reduction in overall accuracy. Predictive policing systems flagged minority communities disproportionately, and post-processing calibration reduced bias in flagged individuals, though criticism remained because historical data carried social bias. The material also cites the Amazon hiring tool, the Apple credit card case, and ProPublica analysis of Compass as examples showing the limits of technical fixes alone. Real-world fairness work faces recurring obstacles. Defining fairness changes across contexts and stakeholders, interventions can reduce accuracy or efficiency, historical data can preserve societal inequality, and stakeholders may resist changes that affect profit or operations. These pressures make fairness both a technical and organizational challenge. Involve stakeholders in defining fairness goals, monitor systems continuously, document interventions and trade-offs, use inclusive and balanced data, test and refine methods iteratively, use fairness dashboards, and bring together ethicists, data scientists, and domain experts in the design process. Fairer AI needs metrics and monitoring. Algorithmic fairness combines metrics, mitigation methods, empirical analysis, and practical tools to reduce bias in artificial intelligence systems. You have seen how fairness differs from accuracy, how interventions work before, during, and after training, and what real-world cases reveal about their limits. Fairer systems depend on measurement, transparency, monitoring, and collaboration.